For the Ethiopian Educational Information and Communication Technology presents Educational Satellite Television Programs.
Hello, teacher. Hello, students. Welcome to today's lesson on molecular orbital theory. Previously, we introduced this topic and learned that the goal of molecular orbital theory is to describe molecules in a way that is similar to how we describe atoms. We learned that when atoms combine to form molecules, the valence atomic wave functions for the bonded atoms are added together. For every atomic orbital, there is a molecular orbital. In today's lesson, we will describe bonding and anti-bonding within molecular orbitals. We will also learn about molecular orbital diagrams. Students, if you are prepared, then we will begin. When two atomic orbitals combine, they form two molecular orbitals. One is bonding and the other anti-bonding molecular orbital. Bonding molecular orbitals have a region of high electron density that lies between the nuclei of the atoms. Anti-bonding molecular orbitals have a region of zero electron density, which is also referred to as a node. This exists between the nuclei as well. As we learned in our last lesson, when two or more atoms combine to form a molecule, their atomic orbitals combine to form united molecular orbitals. The electrons that are in the bonding orbitals contribute to bond formation. The electrons that are in the anti-bonding orbitals do the opposite. These electrons discourage bond formation. When two atomic orbitals overlap end to end, they form two sigma molecular orbitals. Let us look at an example. Hydrogen is the simplest molecule. It is made up of two hydrogen atoms and thus has two 1s atomic orbitals. These two 1s atomic orbitals combine to form two sigma molecular orbitals, which differ in energy and location. As we discussed, the lower energy orbital has greater electron density between the two nuclei. This is the bonding molecular orbital, and it is lower in energy than the original 1s atomic orbitals of the hydrogen atoms. This makes the bonding molecular orbital more stable. The upper molecular orbital has a node in the electronic wave function. The electron density is high, but away from the region between the two positively charged nuclei. The energy of this orbital is greater than the original 1s atomic orbitals of hydrogen atoms. As a result, this orbital is referred to as an anti-bonding molecular orbital. Students, let us do an activity. Please answer the following questions. How do molecular orbitals form? What is a bonding molecular orbital? What is an anti-bonding molecular orbital?
Students, let's get ready. Begin. Time's up! Let's get back to our lesson.
Hello, everyone. Did you find those questions easy to answer? Molecular orbitals are formed when atoms bond together to form molecules. During the process, the atomic orbitals merge to create two different types of molecular orbitals: bonding and antibonding. Bonding orbitals are molecular orbitals that place a high electron charge density in between the nuclei of the atoms. This type of molecular orbital has a lower energy than the original atomic orbitals. Antibonding orbitals are molecular orbitals that place a high electron charge density away from the region between the nuclei. This type of molecular orbital has a higher energy than the original atomic orbitals. Were those your answers, students? If so, great job! Let us continue. Molecular orbital diagrams are qualitative tools that are used to describe the chemical bonding that occurs in molecules. This bonding is explained in terms of molecular orbital theory, as well as the linear combination of atomic orbitals, molecular orbital theory. According to both of these, when atoms bond to form molecules, a specific number of atomic orbitals combine to form the same number of molecular orbitals. The electrons that are involved may be redistributed among these orbitals. Molecular orbital diagrams are quite useful for describing simple diatomic molecules, such as hydrogen molecule, carbon monoxide, and oxygen molecule. However, they are not so easily used for explaining more complex polyatomic molecules, such as methane. Let us return to the hydrogen molecule example, which we were discussing earlier in this lesson. After we apply the two principles of filling orbitals, the Aufbau and the Pauli exclusion principle, we are able to predict that both of the electrons that are in hydrogen molecule will go into the bonding molecular orbital. Molecular orbital diagrams display the relative energy and number of electrons in each molecular orbital. They also show the atomic orbitals from which the molecular orbitals were formed. The red horizontal lines and the arrows on either side of this molecular orbital diagram represent the atomic orbitals involved in the formation of a hydrogen molecule. You can also see here that both electrons, represented as arrows, are in the bonding orbital. The antibonding orbital remains empty in the ground state because there are no more electrons. Students, it is important to note that the number of molecular orbitals that are formed must be equal to the number of atomic orbitals that are available for combination. Molecular orbitals that are unfilled are considered to be present even when there are no electrons in them. Students, please draw a molecular orbital diagram for a dicarbon molecule, as well as a dicarbon cation.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Welcome back, students. Were you able to draw these molecular orbital diagrams? Please compare your drawings to those that are shown on the screen. If you had trouble with this activity and require additional help, please speak to your teacher after the lesson. In today's lesson, we learned about the two different types of molecular orbitals that form when atomic orbitals combine, including bonding and antibonding. We also learned how to describe the orbitals within a diatomic molecule using a molecular orbital diagram. This brings us to the end of our lesson for today. Please note that the next two lessons will be covered without a plasma. Until next time, thank you, teacher. Thank you, students.